This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's get started. So, as always, the lecture starts with a video segment, and today's video segment comes from 1991. And from the group at British Columbia, and it deals with biped walking. So there should be some sound. Okay. So this is passive walk, no motors. Counting on bounds. Careful. Well, maybe we need some motors, right? Okay. So today we're going to start covering kinematics. And kinematics, as I mentioned last time, kinematics is very, very important. The models that describe the robot position, the robot frames and links and joints. So we're going to go over the basics in describing a task, the models that we can use to determine the position and orientation of the end effector. Then obviously when we determine the location of a link, we need to be able to transform that description to the next link, or to describe the position and orientation of the end effector in a previous link. So we need really to handle transformations. Then we need to discuss how we represent the position and orientation. There are many different ways through which we can describe a position or an orientation, and we will discuss few different representations. And I'm going also to describe a little bit what is a manipulator, what is a robot arm, and then what are these joints, what are the degrees of freedom of a manipulator, how we count, represent the position of a manipulator. So a manipulator is defined by a set of links connected through joints. The first of those links is fixed. We call it the base. And the last one is actually this gripper. The whole purpose of the manipulator is really to move this gripper and place it in space to do manipulation. Obviously, later we will see that it is possible to use the body, the links themselves, to do manipulation. We call it whole body manipulation. But for now, we are really interested in locating this end effector, at the same time locating any other links that is moving. So we will see that there are two types of joints that we are going to consider. There will be other possible types of joints, but we can see that any set of joints could be reduced to those two types of joints, the revolute joints and the prismatic joints. A revolute joint allows you to rotate about a fixed axis, and a prismatic joint allows you to translate about a fixed axis. And this motion is done along or about one axis, so it is 1 degree of freedom motion. So as I said, we have links, and those links are in number of n. We're going to call n is the number of moving links plus one base link, the fixed link, and we have joints of two types, revolute joints and prismatic joints. So the idea is we are going to work with 1 degree of freedom, and this is interesting because knowing that we have only 1 degree of freedom joints, then we will be able to connect these to the generalized coordinates, as we will see. And as I said, if we have a joint like a spherical joint, would you know how many degrees of freedom a spherical joint would have? 2? 3, yeah, 3. So what we would do is we will then use 3 revolute joints with 0 links length, and then we will introduce these joints and links to represent a spherical joint. Okay. Now we have this manipulator in this configuration, and the question is, how can we represent the configuration of the manipulator? What would be a good way to represent the configuration? Because we need to know where the manipulator is in space with respect to a fixed frame. So, well, I mean, there are many different ways. We can go to each link and try to fix that link. So we can take maybe a given link and say we're going to locate this link with several vectors that lock it there. So if we use like 3 vectors at 3 different points, the link is defined. And that would give us the configuration of that link. Now we are going to use, in that case, 3 vectors. Each vector has 3 parameters in 3D. So we have 9 parameters to describe each link, and we have n links, moving links, so we will need 9 n's, a lot of parameters. And this would be one of the representations. So the description of the position using a set of configuration parameters can involve a large number of parameters, and each of them is fine. So any set of parameters that describe fully the configuration is called a set of configuration parameters. So in this case here we have 9 parameters per link. Now we are really interested in a particular set of parameters, configuration parameters, that has minimal number of parameters involved. We don't need all these parameters in that 3 vectors, 3 points, because the points are fixed, so there is a constraint between these points, and that is going to show us that these 3 vectors are not independent. In fact, we will see that we will be able to describe the configuration of the link with much, much less parameters. So that brings us to generalized coordinates. So a generalized coordinate is essentially a set of configuration parameters that brings parameters that are completely independent. And working with those coordinates is very interesting because you can use them to find the dynamics later, as we will see. We can use them, we can count them, and the number of generalized coordinates gives you directly the number of degrees of freedom of your robot. So let's analyze how many parameters you would need to describe the configuration of a manipulator with a set of generalized coordinates. So we have this manipulator connected through joints, and in order to count how many degrees of freedom we have, what I'm going to do, I'm going to remove the joints. So let's remove these joints. Now you have n rigid body in space, right? If we take one of those rigid bodies, one of the links, how many parameters you need to describe the position and orientation? 6. 3 for the positions and 3 for the orientation. So with 6 parameters, we have a description of one rigid body. Now we have n moving rigid body. In total, we need 6n. Now, let's think about those constraints introduced by the joints. If we put back the joints, we are going to introduce constraints. Now, a joint has 1 degree of freedom, right? We said 1 degree of freedom. So how many constraints the placement of a joint is going to introduce? Each joint will introduce how many constraints? 5, exactly. Because it is going to allow only 1 degree of freedom. So if we think about the number of constraints, we will see that we will have 5 constraints per joint, and that leads to 5n constraints. Yes?
So would it matter if it's a revolute joint or prismatic joint, whether it's a position parameter or an orientation parameter that's free?
Well, let's look at it. So if we have a joint, it's going to introduce constraints on the rotations and the position. So if we place a revolute joint, it's not going to allow any displacement. And it's not going to allow rotations about orthogonal axis to the axis of rotation. So that's 5 constraints, 3 positions constraints, and 2 rotation constraints. In the case of prismatic, a prismatic joint is not going to allow any rotation. It's just translating, and translating about 1 axis, so the 2 other axes are eliminated. Doesn't matter. It is still 5 constraints. So now let's do the count. So we said we have 6n parameters before placing the joints, and now we place the joints and we have 5n constraints. So the question to you, how many degrees of freedom? It is going to be it is going to be the difference, right? So 6n minus 5n, the answer is n. Okay. So indeed, we have just n degrees of freedom, which is really nice. If we have 1 degree of freedom joints in a manipulator, in a robot, we can be sure that we are going to have n degrees of freedom, the number of joints. Now, I'm talking about a manipulator with fixed base. If I take a humanoid robot and I do the same things, at a given configuration, if we lock one of the feet of the humanoid robot, this is correct. But a humanoid robot can move. So in that case, the base is moving, and the base has 6 degrees of freedom. So it will be n plus 6. Unfortunately, those last 6 degrees of freedom of the base are not actuated. There are no motors. And that's what makes the control of a humanoid robot very hard. However, in the case of a manipulator, if the base is fixed, we have n degrees of freedom for n jointed robot. Okay? Clear? Okay, so let's go to the end effector now. The end effector is this last rigid body in the system, so it has all the freedom before to position and orient on the end effector. So we can think about a point at the end effector that we are locating, and we can think also about the orientation of the end effector, how we orient this end effector, so there is a sort of frame attached to the end effector rotating with it, and that allows us to describe the position and orientation of the end effector. So if we have just one end effector in the robot, essentially we have just one rigid body. At most we need, depending on the freedom, because some robots can only move in the plane. Some robots can move with the restricted rotations or orientations or positions. So at most we are going to have 6 degrees of freedom for the end effector. But again, we can represent that freedom of the end effector, that is the configuration of the end effector, with many different parameters. So we can talk also about configuration parameters for the end effector, and we can see that some of those parameters can be dependent, and when they are independent, they form a set of generalized coordinates, and then we can have a description of the end effector using a set of generalized coordinates, task coordinates, or what we call operational coordinates. So if they are just configuration parameters without the condition of independence, then we can talk about these M parameters describing the position and orientation of the end effector. So this is the definition, that is, we have a set of parameters describing the position and orientation with respect to a fixed frame. Let's see. Give me an example. Any example of set of parameters that describe the position and orientation of a rigid body end effector. So to describe the position and orientation of a rigid body, this is a rigid body. Here is a rigid body. I would like to describe the position and orientation with respect to this frame. So,
well, for the orientation, sometimes tilts, yaw and roll.
okay, you use 3 angles. So if we use like 3 Euler angles or fixed angles, we can find this position orientation for the end effector. And for the position, x, y, and z. So we can take a vector and locate one point, fixed point. So with one vector and 3 angles, we can describe the position and orientation of the end effector. Yes?
Isn't that 6 parameters?
Perfect. 6 parameters.
We use it 5, right?
Oh, I was talking about how a joint introduces 5 constraints on a rigid body. And instead of, so a rigid body, so imagine the base, imagine the next rigid body, it was free completely to move, and now I put a joint, and now it has only 1 degree freedom left. Yeah. So here we have a very nice example of a representation that is minimal representation. So anyone can give me a representation that is not minimal.
Coordinate of 3 points, fix 3 fixed points.
Select three vectors to 3 different points. That will be 9 parameters. So that would be a set of configuration parameters. Well, we will see also that, have you heard about Euler parameters? How many of them you have? 4. So quaternion, or well, the reason we will see later that when we use 3 angles, we have a problem. We have a problem tracking this rotation continuously. There are configurations where the representation becomes singular, and we need a different set of parameters really to keep track of the orientation, and we introduce Euler parameters. Have you heard about direction cosines? No? Vaguely? Okay, you heard about rotation metrics. We're going to see this in a few minutes, but you heard about rotation metrics, right? So you have a frame, and you're looking at the relationship between the two. Well, the rotation matrix, if you take this rotation matrix between 2 frames, so the description of this frame with respect to a fixed frame, essentially, if you take this matrix, which is 3 columns of 3 vectors, so it's 9 parameters. Well, if you take that matrix, these 3 vectors, form the so-called direction cosines of this frame with respect to this frame. And we can use directly that matrix, that description. So we will have 9 parameters only for the orientation, plus the position, 3 parameters. So we will end up with 12 parameters describing the end effector. And we will see why we will go that way, or why we go to Euler parameters, and we will examine those singularities of the representation. So a particular set of coordinates that we are interested in is this set of independent coordinates. We call them operational coordinates or task coordinates. Essentially, there we are looking at the operational point where the robot is acting, where we define the task. So, for instance, the task could be, if I'm going to grasp, the task is somewhere in the middle between the two jaws. As I move, this is the point I'm controlling. But if I have a tool, the task will be here, and the operational point would move depending on where I'm going to do the interaction. So this is the first definition, is operational point. So you have 3 degrees of freedom, and then you add 3 degrees of freedom, like the angles, the 3 angles, to form a set of independent parameters, and that gives you a set of generalized coordinates or operational coordinates. So this number, so before, you remember, it was m if it was not independent. When it is independent, we call it m0 to point that this is independent set of parameters. And that gives us, again, the number of degrees of freedom of the end effector. So an end effector of a robot with 6 degrees of freedom moving in the 3-dimensional space, the end effector itself can be positioned anywhere and oriented anywhere, so it has 6 degrees of freedom. And that is the most number of degrees of freedom it can have. Now, if we go to the plane, if we have a robot that is moving just in the plane, how many degrees of freedom you expect to see for the end effector? My planar robot, it's moving only in the plane. It cannot go out of this plane. For the position, how many we need in the plane? 2, x and y. And for the orientation, 1, only 1. So 3. So if we have a planar robot, then we will be talking about m0 equals 3. And you have different robots with different characteristics that ends up to gives you m0 that is equal to 4 or 5 or 6. But at most you have 6 for one end effector. So now we defined operational coordinates or task coordinates. We defined joint coordinates. And here is an example. If we take a planar robot, so just 3 revolute joints, theta 1, theta 2, theta 3, and this robot is moving in the plane, so we have sort of representation of the joint. So for here you have I don't know, 80 degrees, 45 degrees, and 50 degrees, representing this configuration of the manipulator. So one way to think about it is to go and represent this whole manipulator as a point in a 3-dimensional space, and that space is theta 1, theta 2, theta 3. And that would be the joint space where this point, theta, which is the vector theta 1, theta 2, theta 3, represents the configuration of this manipulator. So we call this the joint space or the configuration space. And this space plays a very important role in motion planning. We talk about configuration space, and we talk about planning motions in configuration space, so planning the motion of theta. And we talk also about all these obstacles that we have in this space, in the physical space, that we map to that space, that becomes configuration space obstacles, or C obstacles, that represent the how obstacles in the real world are mapped to that abstract configuration space. And then we can do the planning around those obstacles. Now, for the end effector, we, as I said, we locate the end effector with a vector xy, but that doesn't define completely the position and orientation of the end effector. We need also to define the orientation or some angle. So we need alpha, and then X, Y, and alpha represent fully the position and orientation of the end effector, and that defines the 3 coordinates, operational coordinates for the end effector. And obviously we have with that a space, the operational space, which is now the combination of X, Y for this example and the orientation alpha of the end effector, and that is a point. So the robot is reduced to a point theta in configuration space, and its end effector is reduced to a point X, Y, alpha in the operational space, and that represents the manipulator and the end effector. Now, these two spaces, so the first space is fully describing the configuration of the robot. But imagine that we add one more joint on this robot. The end effector is fixed, but the robot configuration can vary because of the redundancy we introduce by adding one more joint. So redundancy, in this example here, you can see we have 4 joints, and the end effector still has 3 degrees of freedom. So for the same configuration, you have different possible configurations of the structure, of the links. And that means we have redundancy. So we talk about redundancy, and we call the robot redundant if the number of degrees of freedom of the robot, n, is greater than the number of degrees of freedom of the end effector, m0. So if we have this situation, m0 here is equal to 3 and n equal to 4, then the robot is said to be redundant. And redundancy is very important in order to reach and have accessibility. You cannot just work with the motion of the robot with, for instance, 3 degrees of freedom in the plane. You're going to hit obstacles. So when you have redundancy, that helps you to move around obstacles and position the robot in different configurations. And we measure the degree of redundancy by the difference of n and m0. Okay? So essentially, we're not going to really discuss redundancy, which is very important, but we're going to focus on non-redundant robot first. In fact, in spring we will cover extensively redundancy. We will talk about the use of redundancy to control the robot, make use of the mechanical advantage, the dynamic reduction that is introduced by redundancy, and also the motion planning in collision avoidance using redundancy, and how we combine and control redundancy in a way that would allow us to achieve a task while redundancy is maintained to achieve different criteria and different goals. So redundancy, we will not come back to it in intro to robotics, but it is a very important notion that you need to at least know about in terms of its definition. What we're going to do, we're going to go to the basics now, and we're going to start by building the models that would lead to the forward kinematics. So I'm going to start with the simple definition of a vector that is defining a point in space, and we are going to go from there to building the models for representing an object in space, which requires position and orientation, and then we connect these objects. But before that, we will talk a little bit about representations of those different parameters I mentioned earlier. So we will talk about Euler parameters, we will talk about Euler angles and direction cosines, and probably this week we will cover all of that. We will cover transformations, how we move between frames, and we will be ready next week to build the forward kinematics. So a point in space, P. How can we define a point in space? And what are the things that really fix that point or define it with respect to some reference? So So what is really important is to think about a point is the fact that the definition of a point, every one of you probably think vectors, right? We can use a vector to define the point. But what really is going to determine the vector is another point, a reference point, the origin that you're using to define the point. If you change the origin, you will change the vector. So we will talk about the description of a point with respect to another point, to some origin. And this point is going to be represented by a vector p. And this vector p will describe this point with respect to this origin. If we change origin, we will change the vector. Okay? So if we have 2 points, we define again the origin, and then we will have 2 different vectors representing this point. And these are those vectors built by taking the connection between the origin to the point. Very simple. Now, I'm insisting in this because now we're going to introduce this origin, and then we will be able to describe the vector component. So the vector is independent of this, x, y, and z, which frame we are taking. Now we're going to put a coordinate frame, and then we can express this vector in that frame. If I change the orientation of the frame, the vector is the same. The coordinates, the components of the vector will change. And we're going to be interested in those transformations between different descriptions that involve different frames. We will work with orthonormal frames, x, y, and z, and we will go from one frame to another. So in this case, x, y, and z, and we did a small rotation, and so about the same origin, and we ended up with a different frame. And we need to know how we can take a description of the coordinate of p in the frame x, y, and z, and then go to a description in frame x prime, y prime, and z prime. And this is going to happen using transformations. Now, this transformation is just rotating the frame about the same point, but we might have a prismatic joint, and then we are going to translate the origin. So there will be a translation. So we need not only to deal with rotation in the frames, but also translations of the frame. Well, a frame really is related to something beyond a point. The fact that if we just we're working with points, we just don't need really to worry about the whole orientation. What is really happening is that you have different points on a rigid body, and when we rotate, we are keeping the distance, but the orientation is changing. So a frame is really related to the description of a rigid body. So if we take this rigid body, take a fixed point, and attach to it a frame. I'm calling this frame B. So the coordinates are going to be described with respect to those axes xb. So this is the frame B. We denote xb, yb, and zb, and the frame itself is B. And the question is how we describe the frame B with respect to a fixed frame A. So, as you know, we need to find the relationship between the origins. So there is an origin of frame A, an origin of frame B. We need this vector between the two. And that is defined by a vector. And this vector is going to locate the origin of frame B with respect to frame A. And we have its description in frame A. So this is PA. The orientation of the frame is these vectors xb, yb, and zb. These vectors can have descriptions in different frames. Now we are describing them in frame A, so xb in A, and this is the notation. We denote xb, and here we put A to say these are the coordinates of xb in frame A. So these vectors are going to describe the rotations of B with respect to frame A if it moves. So essentially, if you think about those vectors and the relationship with the frame A, we really going to find the rotation matrix, which is the first model that we need really to use in order to describe the rotations of one rigid body with respect to another rigid body. So because we are concerned with just the rotations, I'm going to slide this frame and make PA equal to 0. So we will just move to the origin and just think about the rotation. And in this case, we will focus only on the rotation matrix and the rotations of that frame with respect to frame A. So we are now concerned with the rotation of frame B with respect to frame A. This rotation is described by a matrix. It's called the rotation matrix, and it has 9 components. We are calling them R11, 21, 31, these 3 columns. Okay, I know some of you know very well the rotation matrix. How many of you knows perfectly the rotation matrix? I remember. How many of you remember? Okay. All right, this is very important, so pay attention. Those of you who are seeing this for the first time, but I'm sure everyone has seen it in some form or another. So what I'm going to do, I'm going to state a description of what is the relationship between xb, this vector xb, and xa. xb defined in frame B is obtained by this rotation matrix, and the vector, the resulting vector, is xb in frame A. So the description of xb in B is now transformed into a description of xb in A using the rotation matrix. What is xb in B? 1, 0, 0. The x vector in its own frame has 1 unit along the x direction, so it's 1, 0, 0. So what about y? It is the same thing, 0, 1, 0, right? About z, 0, 0, 1. These are the unit vector x, y, z in their own frame, right? And now, using the rotation matrix, we have the description, we have their component in the A frame. So the rotation matrix is basically just this, right? I'm just using that definition. So if you multiply, the first column is xb in A, the second column. So what is the rotation matrix? The rotation matrix between B and A is simply the component of xb in A, component of y in A, and component of z in A. Okay? So always remember this definition. This is very, very important because we are going to find the rotation matrix through many different ways. But sometimes you are looking at a problem and you are looking at the frames. Look at the component of that frame in the other frame, and you will make sense of your result. And this is always the definition. The rotation matrix, essentially the columns of the rotation matrix, are the component of the axis x, y, z of the new frame in the reference frame. Okay? All right. So this is the definition of the rotation matrix from B to A. It is xb in A, yb in A, and zb in A. So how do you obtain xb in A? How do you obtain the component of xb in frame A? You just do the dot product. So essentially, if you do the dot product of xb with x, y, and z, you will obtain xb in A. Right? You agree? Good. So which means the rotation matrix is essentially the dot products of xb with x, y, and z, yb with x, y, and z, zb with x, y, and z. Right? Okay, good. So focus on this and look at this row. Do you see anything like special? So here you have x, 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 y, z. Here you have anything constant? xa, xa, xa. So it's the dot product of xa with xb, yb, and zb, which is, you see this? Which is xa and b written as a row, which means it's transpose. This is very interesting because if we start looking at these properties, we see that this rotation matrix is either the component of B in A or the transpose of the rows of A in B. So B in A in B. Inverse relation. Going from B to A, going from A to B. So going from A to B, we are able to see that it is just the transpose, which means that B to A, the rotation from B to A is equal to the transpose of A to B. A to B is the inverse of B to A. So we have this property. If I'm trying to compute the inverse of the rotation matrix B to A, which means it's A to B, it is simply B to A transpose. So the transpose of this matrix is simply, the inverse of this matrix is simply its transpose. And that's a very important property. And this property comes naturally because the rotation matrix formed with these unit vectors that are orthogonal. So the matrix is called orthonormal. And this orthonormal matrix is always going to have this property. Its inverse is its transpose. All right? Example. So can you compute the rotation? I think you have it. Don't look at your notes now for this example. So could you give me the first column of the rotation matrix from B to A? What is the first column going to be? So it is the component of XB on A. And XB on A, you see XB and XA are aligned. So anyone who could say what are the components? So 1, 0, 0. What about Y? Y has a component only along the Z-axis, right? Y is only along the Z-axis, and 0 about the others. What about Z? Z has a component along the minus Y-axis, and its full component -1, 0, 0. Very simple example, but it illustrates what we have done. Essentially what we are doing either dot product between the two vectors or looking at the component of that vector in frame A. At the same time, if you think about this, this is XB in A, YB in A, and ZB in A. This is our definition. And in the other direction, if you look, it is XA transpose in B. So if you take XA and express it in B, it's going to be 1, 0, 0 transpose. So these rows represent XA A in B, X, Y A in B, and Z A in B. All right. So now we know the rotation matrix. Let's build finally this representation for a rigid body. So we know how to represent the frame, the rotation of the frame. We need the translation of the origin, and by combining X, the description of the rotation, that is those vectors, and by locating the origin of the frame B with respect to A, we are going to define fully the frame B with respect to frame A. So the frame B is essentially defined by this rotation matrix B to A and by the location of the origin with respect to A. Okay. So there is different ways of thinking about the use of those rotation matrices. And in fact, we can think about it as we have done so far, which is to say we have a vector P, we have a frame A and a frame B, and essentially we are expressing the component of frame B in frame A, in frame B, and we are looking at the relationship between the two. So this is what we call mapping. That is, we are changing the description of a vector from one frame to another frame, but the vector remains the same. There is another way of thinking about it, which is, so this is the way we are looking at it. You have a vector P, and this vector P is going to be described by its dot product with A to give you its component in A. And this is the same thing. I'm just removing the vector outside and putting it as a matrix. So X A transpose Y and Z transpose. You see this writing? It's the same writing, right? Here I'm doing dot product, and just if you move P outside, it means you are doing that multiplication with the different rows. So now, if you have this relation, you can say P can be expressed in any frame. I mean, this operation could be represented in any frame, which is, let's select B, the frame B or C or D. So, but you have to be consistent. You have to take the same description. And if you do that, essentially you are obtaining that mapping. That is, you are obtaining P in B rotated to give you P in A. So this is changing the description of the same vector, P, from one frame to another frame. In the translation, we are going to start by considering the same problem, but while maintaining the same orientation of the frame. So I'm going to slide this frame and change the location of the origin of the frame. So frame B and frame A has the same orientation, and we're going just to move along the direction of the vector P. So if we have a vector, if we have a point in space, it is located with respect to origin B and described by the vector P. The same point in space is described with respect to another origin A with a different vector PA. So it is the same point but described with respect to two different points, two different origins attached to two different frames, and you end up with two different vectors. So this was our initial description in frame B, and now we have a new description, and this transformation is resulting in two different vectors. You have to realize, contrary to the case when we were doing just rotations, now when we do a translation, we are going to change the description by changing the vectors involved in the description. So this operation that involves a translation of a vector P defining this origin of the frame B, it's changing the description from origin B to origin A. And the relationship between the two, that is the relationship between the green vector and the red vector, is essentially this relation that is giving us the vector with respect to A, origin A, as the sum of the vector with respect to origin B and the translation of the origin. So this fact that we have now two different vectors is going to appear later in the homogeneous transformation and make the transformation a little bit different from rotation matrices, because we are introducing a translation and we are introducing this non-homogeneous relation in the model. So when we come to a general transformation, so now I'm saying I'm going to have a description of this same point P, but with respect to an arbitrary frame B that is rotated with respect to A, then we need to account for this rotation, and that means that in the description here, it's not simply the sum, but I have to do the sum with respect to descriptions in the same frame. That is, I cannot add this vector directly with this vector. I need to rotate this vector to frame A. And that means we have this relation, this general relation, that is, we take the description of P, we rotate it to frame A, we have its description of A, and we have the origin description of A, and now we can add them together, and the result is this vector. We haven't changed anything. We still are talking about this vector plus this vector equal this vector. But what we have to make sure is that this description is rotated correctly to frame A. All right, well, this is the general transform, and in fact, using this, applying this between links, we should be able to compute and propagate, go from this link to the next, to the next, to the next. But this description is not simple to carry when you have multiple links, because you don't it's not like a rotation matrix, where with a rotation matrix, if you know the first rotation with the frame with respect between two frames, and you know that the two are rotated with respect to a different frame, all what you need to do is to multiply the rotation matrices. In here, you have to carry sums, and you have to carry those relations. So a better way to handle this transformation is to try to put it in a homogeneous form. How can you do that? This is sum of two vectors in three-dimensional space. You cannot have it in a homogeneous form. But if you go to four-dimensional space, then you can put it in a homogeneous form. Do you want to see how? Yeah? Okay. So I'm just rewriting the same thing, and I'm going to just add one more row for nothing. So this row is saying 1 is equal to 1, right? If you multiply this vector by this matrix, you obtain the first relation, right? And the second part is 1 equal to 0 multiplied by the vector P plus 1, so 1 equal to 1. But now we have captured the homogeneous property, that is, this vector is transformed into this vector, this description is transformed into this description using the rotation matrix and the translation. Do you see that? And this is what we call the homogeneous transformation. It's a 4x4 matrix. You have 4 components that are doing nothing. except help the math to make this transformation homogeneous, in that when we go from A to B to C to D, then essentially we are going just to multiply matrices. But we have to handle 4 by 4 matrices instead of 3 by 3 matrices. Okay, so this is a very important component. Now, by the way, sometimes 0001, the definition is on the top. So sometimes you define 1p instead of, but it is exactly the same computation. So here is an example of the homogeneous transformation. Now we have 2 vectors. I'm taking the frame. You remember the frame the example we saw earlier. The example where we had a rotation matrix with rotating about the x-axis. So I'm just translating now the origin of B with this vector 0, 3, 1. So the homogeneous transformation, so it is the same rotation matrix as before, and 0, 3, 1 is the vector describing the origin of frame B in frame A. And your homogeneous transformation is here. And now, using this homogeneous transformation, you can compute the new position of the point P. So the point P in frame B is described by 0, 1, 1. This is the point I'm looking at. And to find this vector, all what you need is to take this transformation and multiply this vector by this transformation. But you have to add 1. So we take the 0, 1, 1, we add 1, and the multiplication leads to 0, 2, 2, and 1. You drop the 1. The answer is 0, 2, 2. So if you look over there, this was happening in this plane. So essentially here we have 1, and this is 2, and 1 and 2. So it's just 2, 2. Okay? Clear? Okay. Now that you understood everything, I'm going to confuse you. Normal. I mean, once you understood mapping, now we have to completely change the intuition. Now, instead of mapping, we're going to so a rotation matrix, I said, allows you to describe the same vector in 2 different frames. But now I'm going to take the rotation matrix and use it to rotate a vector. So the vector was here. I'm going to rotate it by the rotation matrix. So I said the mapping is changing descriptions. Okay? An operator is moving those points in space. Well, that could be useful. So you have a vector, you have one frame, you have a description. Another frame, you have a description. Now, what I'm going to do a rotation, and this rotation will rotate the vector. So, in fact, a rotation matrix, which could describe the relationship between the component of the same vector in 2 different frames, in this way, can be also used as an operator that would operate on a vector P1 to produce a vector P2. And this is very useful later when we compute representations. You will find very useful to compute transformation between different frames. So R here is operating on P1 to produce P2. Okay? So P2 is the rotation applied to the vector P1. And of special interest are those rotations that take place about some specific axis, like the x-axis or the y-axis or the z-axis with some rotation. So then you can talk about Rx with some angle theta, and that will be very useful in some of the operations. So in general, we can talk about a rotation about a k vector, not the x, y, z, but any arbitrary vector. and it rotates a vector P1 into a vector P2. So here is an example. This is a rotation about the x-axis. So the x-axis is 1, 0, 0, and the rotation about the x-axis is of theta. It is cosine theta minus sine. You know this familiar matrix, rotation about the x-axis. So if you take P1, which has component on y and z, so it's 0, 2, 1. 0, 2, 1. If you take this matrix, you end up with 0, 1, 2, which is over there, 1, 2. You see P1 and P2? So this is the vector 0, 2, 1, 2, and 1. And now 0, 1, 2 is 0, 1, and 2. Okay. Translations. The same thing. We can now, instead of describing a point with respect to two different frames, we are going to translate that point using an operator. So in the mapping, we took the vector with respect to B and produced a vector with respect to A. In the operator, so in the operator, this is what is happening. We are changing the point. We're going from P2 to P1. So this point P1 moved. So we have two different points and two different vectors. So when you are translating, you are thinking about it like in the rotation. The rotation, we had the vector. We have P1. We rotate it to P2. Now we have here a vector P1 with this translation is essentially producing this point. So I have to remove this. You can see it better. So we are moving P1 to P2 with the translation Q. So P2 is P1 plus Q. So this is an operator of translation. And you can have this operator Q along the x-axis, y-axis, z-axis, or any arbitrary vector. So a translation through the operator Q would result into a different vector P2, and now you have to describe it. You can describe it in frame A or any other frame, but through always maintaining the same relation, same description for all the vectors. When you apply the components for describing the frame, you have to make sure that Q is described in the same frame as P1, and the result will be in the same frame. So now we can think about this operator as this operator 1, 1, 1. That is, there is no rotation at all, but there is only translation Qx, Qy, Qz, and this is defined by the Q vector. So the translation is done by Qx, Qy, and Qz. And now you can combine the two. You can combine the rotation and translation, so you could have an operator operating by translating and rotating. So the general operator that you can imagine is this operator rotating about some vector k with some angle theta and translating q. So the point P, which was in P1, now is rotated and translated. And the result is P2. And this is without any definition of the frame. Then you define the frame in which you want to express all these vectors, but you have to make sure that you are using the same frame for all the operations. So this is the most general form of transformation between two different points. It is the same homogeneous transformation. It is the interpretation of that transformation, whether it is changing the description or operating and changing the points. Okay. Are you enough confused? Good. So two things. We saw the transformation. It is the same homogeneous transformation that has two components: rotation, translation. Rotation matrix, translation of the origin of those frames. And that can give us mapping, changing the description. And I just discussed the other interpretation that you could have, which is to change the vector itself. And that means change the points describing those rotations. So when you rotate a vector, you are going from one point to another point, or when you're translating, you are going from one point to another, and you can apply both of them. And now we're going to look at the inverse. Now, in the case of rotations, the inverse is very simple. What is the inverse of R, rotation matrix from B to A? Transpose. Now, for the homogeneous transformation, this is not the case. We cannot just say it is transpose. That is, this matrix is not orthonormal because the presence of this translation. So the inverse is not exactly the transpose of this matrix, but it is almost, because if you look at the inverse of this matrix, it involves the transpose of, because if you take it by block, you will see that you have the inverse here. This is the same. The only thing you have here is the description of the inverse of this vector. What is this actually? I mean, if we were thinking about this inverse, it is going from A to B. So this is the origin of A in frame B. So basically, you are just writing here the origin of frame A in B. That's it. Okay? So now we know the forward, we know the inverse of the homogeneous transformation, and it is going to be essential. The homogeneous transformation, we're going to use it to describe the kinematic chain of the manipulator, and we will see that this transformation could be described by those 4 parameters, the DH parameters. So we will be able to describe each relation between successive links just using 4 parameters, the DH parameters. So I will not reveal the movie segment for next time, but unless you have any questions, we can stop here. Any questions? No? Okay, we will stop here and we'll see you on Wednesday.